Hey, and welcome to another video in kinematics. Last time we got our first look at a velocity time graph, or more accurately, a speed time graph, but today we're going to be taking a look at a velocity time graph, and specifically, what's the information we can get out of it. I mentioned previously that the slope is going to be the acceleration, but let's go ahead and take a look at that. We defined acceleration as the change in velocity over the change in time. And I even did a little fancy hat. But if we look at our graph, my velocity is on the y values, and my time is on the x. So this is the same thing on this particular graph as saying delta y over delta x, which is our slope. So if I wanted to take a look at this first section here, my acceleration or my slope is going to be y2 minus y1 over x2 minus x1, which I can just use the endpoints here and here and plug them in. This point is 2, 2, so I'd put in 2, 2, minus, 0, 2. In this case, that gives me 0 over 2, which is still 0, and the units for this would be then meters per second over seconds, which would then simplify to 0 meters per second squared. So again, we find that the slope of a graph is helpful in understanding and identifying what's going on with it. And we'll also note that the meaning of a flat section has changed. Whereas on a position time graph, this flat section over here would be where it's not moving. On this, it's still moving. It's moving at a constant speed of 2 meters per second. This graph, this flat section means constant speed, no acceleration. Whereas if we want to look at the acceleration of a different section, say this one here, my acceleration would still be y2 minus y1, but I'd need different data points. Still going to be the slope, still going to be useful, but just different values. So in this case, let's take a look here. We can count, we can go down 1, right 1 to get a negative 1 for the acceleration, negative 1 meter per second, or we can plug in our values. We can use any 2 points that touch the grid in here. I could even use the endpoints, but I'm just going to use these two. 3 and 2, and 2, 3, which gives us negative 1 over 1, which is negative 1 meter per second squared. Simple and easy. Okay? So understanding these graphs is fairly easy. Okay? But when are we staying still? What are the things we knew about previous graphs? Well, let's just kind of go over that again. When is something going forward? When is it going backwards? When is it standing still? Okay, these are all questions that we need to be able to ask. So let's go ahead and get them. We'll start with going forward. Okay, going forward indicates you have a positive velocity. You're moving towards or forward from your starting point. So what we need to do is we need to find out whenever our velocity is positive. Now, when we did this on the position time graph, we did this by looking at the slope, looking at when his slope is going up. In this case, we have the velocity directly measured. All we need to care about is when is the velocity positive? When is it above this line here, which is any point up to this point. Everywhere here that is I am covering in red, poorly in some cases, is where there is a positive velocity. You are moving forward during this time. Whereas if we want to talk about going backwards, that's when you have a negative velocity, when you're going in the opposite direction, which would be any point. I'm covering in blue now. And if we want to talk about standing still, that'll be any time you are at 0. Okay, so anytime you're at 0, no matter how briefly that is, you are standing still. Let's go ahead and recolor code this graph for you. So we can figure out when something's going forward, we can figure out when it's going backwards, we can figure out when it's standing still. We can figure out all this. We can figure out what the velocity is. And we don't even have to calculate the slope, we can just look at the graph. What's the velocity at 1 second? Well, we go 1 and that's 2 meters per second. What's the velocity at 6 meters at 6 seconds? Well, we go find the graph, it's at -1. We can just find it by looking at it. We can find the velocity, we can find when it's going forward, when it's going backwards, when it's standing still. The only thing we can't do, or haven't talked about doing yet, are figuring out what the displacement is and what the starting position is. And spoiler alert, we can't do starting location. Just can't. But we can find the displacement. And we're going to do that. We're going to have to start over here. So let's clear this screen and come back. Not too long ago, we defined velocity as the change
in position
over your change in time. If we rearrange this, multiply both sides by time, cancels out over here, we get instead delta x, or your displacement, equals velocity times time. And this is where we can get clever. Because if we look at this graph, on the x-axis we have time. So this thing right here is our time. And then on our y, we have velocity. So this section here is velocity. Well, let's just shade in this region entirely that encompasses. This region here, this boxing region that I'm going to shade in a little more thoroughly now, represents the delta x because it is velocity times time. Velocity being our y values, time being our x values, which means that if we can find this box, we can find the displacement. Or more accurately, if we can find the area between this line and the x-axis, we can find the displacement. A common term for this, if you take calculus, is the integral. We take the integral of the velocity graph. We find the displacement. Now, I'm not expecting you to do calculus, but I am expecting you to be able to find the area. Area of a square or a rectangle is just base times height, or v times t. So in this case, this is 2 wide and 2 tall. Always remember, you got to be between the line and the x-axis. So in this case, in the first 2 seconds, delta x equals 2 times 2, or equals 4. Okay, that's pretty cool. That's pretty useful. Let's say if we wanted to look at a different chunk. Let's say we want to look between 0 and 4 seconds. This is 0 to 2. Let's do red for 0 to 4. Well, our delta x is still going to be the area here, but because my area now is a different thing, it's this red area, I need to go about it a little differently. Now, there are 2 schools of thought of this. The first is, well, I already have this rectangle, all I need to do is figure out this triangle. Or I can go, well, this is a trapezoid. Either way works. Take your pick. I'm going to be lazy and just find this area and then add it to the first one. Regardless, just break it up into chunks and go from there. So 0 to 2 we said is 4, so let's just do 2 to 4. Well, it's a triangle. So instead of being base times height, it's going to be 1/2 base times height, which in this case is 1/2 times 2 times 2, or just 2 meters. So for this section between 2 and 4, the area is 2, which means the area for this entire section is 2 plus 4, or 6. And that's how we get our displacement from this. With the velocity graph, we can do everything we did with the displacement graph, except find the starting position. So let's go ahead and take a look at a blank problem. So looking at this graph, again, we've done everything we need to at the top left, but we haven't touched this section down here at all. So why don't we have you, on your own, find the displacement of, let's just say, between 5 and 8 seconds. find this area's right here displacement. Go ahead and give it a try and come back and check your answer after you're done. Now, if you did this carefully, you would have said, well, this is 3 wide. And you would have said, this is -1 deep. How do I get -1? Well, it's -1 over here. Please remember to keep your signs. -1 times 3 equals -3 meters. I gave this to you because it was a little tricky, intentionally to see if you're thinking about it a little bit, but also to make a point. You can have a negative displacement. You can have a negative velocity. It just means you're moving behind or backwards. If you start here and go this way back, that's negative displacement. Whereas if you start here and go this way, it would be positive. Negative, positive. It's all relative to how you look at it, how you think about it. So be careful with such things. Anything that is below the axis, like this entire section here, is going to give you negative values. So let's go ahead and back this up really quick. I already told you that this section is -3. And we know from our previous work that this entire section up here is 6. Find the entire displacement of this object over the entire 10 seconds. So starting from here to here. That means you'll have to find this area and this area and add them in. Go ahead, give it a try on your own, check back. Okay, if you did all your math, you'd get that this section here is half. Don't forget the half for a triangle. And don't forget the half for the triangle over here. So you get 6 minus a half minus 3 minus 1. So after these 10 seconds, if the object followed this path, it's only 1.5 meters ahead of where it started at. All right, let's take a look at another fresh one. And you'll do this entire one from scratch.
Okay, here we have a sample problem. With this velocity time graph, I want to know what is the acceleration on part A where it's pointing, which is here. What is the acceleration on part B? And then what is the displacement of this graph all the way through? In order to do that, what you might have to do is mentally break them up into sections of things that you can measure, like this triangle or this rectangle here. But calculate all the different areas and then add them together. Don't forget, below the x-axis is always negative, and you always want to go between your line and the x-axis. So like I did here is what you want to do. Go ahead, give that a try, check back after the pause.
Okay, if you did all your math, the acceleration on the first section here would be 2 meters per second squared. You find that from your slope, you can either by counting, for every 1 we go over, we go 2, we go up, or you can plug it into the slope formula like I did here. The flat section is just going to be 0. You can know that automatically, or you can go, well, for every 4 seconds I go over, I go 0 up, or you can plug in the slope formula. The displacement's a little harder. Each of these sections you'll need to split up. But if you do that in each section, you'll get all these values, then add them together to get a total of 6 meters.